All right, so welcome to week 12. Homework 8, I had it originally due on Monday the 16th, but I changed it to Wednesday the 18th. That way when we meet on the 18th, if you have any questions, like last minute ones, we can talk about those. Homework 9, I assigned a little earlier today, not due until December. The reason is there's Thanksgiving break. More about that in just a moment. But it's up there. You can take a look at it. It's over chapter 8 and then parts of 14 through 16, actually. So today we'll finish up talking about chapter 7, hopefully. Move into chapter 8, where we'll do the first 3 sections of chapter 8. And then we'll jump up to chapter 14, actually. Okay, so a little bit out of order. And chapter 14 is on simple harmonic motion. I think you're going to like it. The lab tomorrow is just for Group B. So Group A went last week. Group B will be meeting here tomorrow then for the lab that we're doing. It's called the human arm model. And I thought I'd put together a little calendar here of the next several weeks. Any questions on the first 3 points up there, first of all? Okay. So this goes Sunday through Saturday. It's a calendar. So today's the 11th. Again, we'll finish up talking about chapter 7, move into chapter 8. And then next week is a regular week again. Monday, I'll give you an online thing to watch like we've been doing. So Monday online. Wednesday we'll meet in person. And then Thursday of next week will be Group A. And we'll be doing a simple harmonic motion lab. So next week we'll be talking about things like simple harmonic motion, waves, standing waves, like a little bit about guitar strings and different sounds you could make from that. Okay, so this week, this is next week, and then the following week is a short week. It's Thanksgiving break week. So we will not meet in person on the 23rd. Again, I'll have a video for you. And so sort of an easy week, I guess, in preparation for the week after that, which is test week. So the third test already is coming up. And online review on the 30th of November. Then the actual third test is December 2nd. That's when homework 9 is actually due. And then Group B will be doing their simple harmonic motion lab December 3rd. Okay, this is actually the last lab coming up here. Okay, and then just looking ahead, the following week is so-called dead week. We'll be talking about fluids and thermodynamics in preparation for the final, which I'm not sure the date of that yet. I've got to look it up. They didn't have it yet when I put this syllabus together. Okay, so you can kind of see the light at the end of the tunnel, I think, right? I mean, pretty much it's all there on that piece of paper. Any questions or comments? Okay, so hopefully we'll keep to the same schedule. COVID cases are going up. I haven't heard anything about it, but we'll just see how it goes. Okay, so until further notice, that's what we're doing. All right, so I thought we could start with some homework problems from homework 8. Let's see. So we've done a few of these already. I thought we could talk about this one. The crankshaft in a race car goes from rest to 3060 RPMs in 2.8 seconds. What's the angular acceleration of the crankshaft? And then part B here, how many revolutions does it make while reaching 3060 RPMs? Okay, good. So this is kind of the beginning of chapter 7. All right, perfect. So we go from rest. So angular velocity of 0 up to 3060 RPM, and this happens in 2.8 seconds. So this 3060, what does that represent? That's the frequency, just not in SI units. 3060 revolutions per minute, we need that to be in revolutions per second. So 1 minute, 60 seconds. 51 maybe. Let me actually punch it in. Good, 51. And that's revolutions per second. Good, so that's actually SI units. I mean, usually you see things in RPMs, but the SI way of looking at it is revolutions per second. The reason I'm doing that is then I can figure out the final angular velocity. This is 2 pi times the regular frequency. So 2 pi and then times 51 revolutions per second. Okay, so I'll actually do that. 2 times pi times 51, 320.4. Okay, and then that's radians per second, because it's 2 pi radians for 1 revolution. Okay, and then I can get the angular velocity. Omega final minus omega initial divided by the amount of time. So I'll leave it to you to put these numbers in. Just make sure that you put this for the final angular velocity, and then the initial is 0. Okay. Good. So that's how you can get the. That's how you can get part A. What's the angular acceleration? Part B is how many revolutions does it make? Okay. So this is one where we'll have to figure out how many radians we go through and then change that back into revolutions. So we've got all the kinematics equations to work with. Let's see if this one will work. So delta theta, omega initial times time, plus 1/2 alpha t squared. So what I want to do is figure out delta theta and then figure out how many revolutions that corresponds to. This is the first equation that popped into my head. Let's see if this actually works. Initial angular velocity 0. Okay, so this term would be 0. 1/2 alpha t squared. Okay, this one actually will work for you. You'll just have to have alpha from the first part. So I'll put check mark. Put the numbers in. You get it. You get the amount of radians. Once you get the amount of radians, here's the conversion factor. 2 pi radians is 1 revolution. So this will come from this here. That's how many radians you've gone through. And then it's 1 revolution for 2 pi of those. So then you can get the number of revolutions. Don't be surprised if it's a large number, right? It's the crankshaft of an engine turning over really quickly. Okay, good. And again, half the battle with this stuff is knowing what the symbols mean, right? So you've got to have some practice and get used to these things. Angular velocity, angular acceleration, delta theta, radians, all those things, you got to keep them all straight. All right, any questions on that one? All right, let's look at a couple more here. Okay, so in this one, balls are attached to light rods and can move in horizontal circles as shown. Okay, so we've got kind of an overhead view of what's going on in the picture. Whoops. There's 1, 2, 3, and 4. And we want to rank from smallest to largest the torques. Okay, so remember, to get an angular acceleration, you have to have a net torque. So that's why we're talking about torques now. Net torques lead to angular acceleration, just like net forces give you regular acceleration. Okay, so the first one you see is some force F over here at a distance r. This is 2F at a distance r, just F at 2r, 2F at 2r. Okay, so remember what torque is in general, and I'll draw this picture on a piece of paper, just a second. Whoops. Okay, so the first one, this is F just at R. The second one is This is still R, it's just not drawn to proportion. Okay, and then this is 2F. The third one is 2R and F. And then the last one is 2R and 2F. So in all the different pictures, F and R are perpendicular to each other. So there's there's 90 degrees between R and F in all of them. Okay, so there's we don't have to consider that. They give you the masses, but remember torque is just R perpendicular times F, right? It would be the sine of theta maybe, but that's already built into R perpendicular. The mass isn't here. They give you the mass in the little pictures, but we don't need the mass. We needed it for a previous problem that had the same picture, but for this one we don't. So the first one, this one, torque 1 would just be equal to R times F. Torque 2, it's R times 2F, so 2RF. And then torque 3, 2R and F, so 2RF. Those actually tie each other. This is just F, but it's at 2R. This is 2F, but it's at 1R, so those torques would be the same. The biggest one is actually the last one here, 2R and 2F. So this one we have 4RF. So the last one there would actually give you the largest angular acceleration because you have the biggest torque. Assuming, again, that these are perpendicular to each other, which they are. Okay? So then you have to actually take them and rank them from smallest to largest. And to do that, you can actually just grab them, move them here, put them in whatever order you need to. Okay? All right, any questions on that one? Okay. What is the net torque in this problem? That'll make it work today. Okay, so here's the picture. You've got the 20 newtons over here. Try to make it rotate counterclockwise, which is actually the positive direction. And on the other side, you've got 30 newtons. Try to make it rotate clockwise, which is actually the negative direction. So the net torque for this problem is going to have to be negative. They don't say magnitude or anything like that, so we'll have to make sure we put the negative sign in here. So 20 newtons at 4 centimeters. Wait a minute. So the 4 centimeters is the diameter. We need the distance to the pivot point. So actually that's going to be 2 centimeters. Okay, let me draw a picture and then we can solve this one. Okay. So this one was 20 newtons. On the other side, 30 newtons. And again, they give you the diameter, which is 4 centimeters. We really need the radius, this distance. And it's the same for both of them, from here to there or here to here. 2 centimeters, divide that by 100, 0.02 meters. Okay, so I can do the net torque. This would be 20 newtons. Don't forget the minus sign because it's, positive really, because it's making it rotate in the positive direction. And then subtract the other one because this makes it go clockwise. And then same distance, 0.02. So negative 0.2 it looks like, Newton meters. What is it? Sorry, Rick? 0.2? Let's check it out and make sure. What's that?
It's right on
0.2, okay, so minus 0.2. Okay, good. Were you looking at the diameter? Okay, yeah. That's good to double check, you know. All right, perfect. Excellent. Any questions on that one? All right, good. All right. Let's see. This is a good one. Okay, so in this picture, you've got a F1 over here at 20 newtons, but there's some kind of angle here, 45 degrees. And then here's F2 over here. And it says, in this picture, F2 acts half as far from the pivot point as F1. Okay, so we don't know how far this is from here over to here. We just know that this distance is twice as big as this distance here. Those forces and the torques they provide make it rotate in opposite directions, so they're fighting with each other. What magnitude of F2 causes the net torque to be 0? Okay, so torque is related to force, but where is the force applied? What's the angle between the force and the lever arm? Okay, so we'll need a nice picture for this one. These are kind of scary when they don't actually give you the distance, but we'll see how it works out. Okay, so we got F1 over here, 20 newtons, and then this is 45 degrees. And then we got F1 over here, this is F2. This whole distance is, I'm just going to call it L. This distance is half as much, so L over 2. Okay, so we'll set it up, and maybe we won't even actually need the length here. Now, if you just said the whole length was 1 meter and that was a half a meter, that would work out fine for you too. They don't say how big it is, it's just in relation to each other. So this force would make it rotate, and the torque it provides would make it rotate counterclockwise. This would make it rotate clockwise, so they're against each other. But they're telling us torque because of 2, that magnitude of torque has to be equal to the torque because of 1. And this is just the magnitude. The magnitude of this equals the magnitude of that. And we can see from the picture they're opposite directions. So this torque 2 would be the force, and then the distance to the pivot point, L over 2. And that's got to be equal to this perpendicular part of the force. So F1 perpendicular. Okay. So F1 perpendicular is F1 sine of 45. Right? That's the perpendicular part of the force. Now they give you 45 degrees, so if you accidentally pick the cosine, you would get the number correct. But it's really the sine, because that gives you the perpendicular part of the force. Okay, so here's the perpendicular part of the force, and then times L. And then the L's cancel out. Right, there's an L over 2 and an L, so the L parts cancel out. And then the only thing that we don't know is what we're actually looking for, which is F2. So F2 turns out to be twice F1 sine of 45. And then it kind of makes sense. This force is half as far away, so it's going to have to be twice as big as the perpendicular part of F1. So that's what that says for us. Okay, 2 and then, let's see, 1.41 or something like that. So 2, and then whatever this turns out to be. So I won't even put this step. I'll leave it up to you to finish that part up. Okay? Very good. Any questions on that one? All right, good. So balancing torques again. So it's kind of neat to look at this. This is twice as far away. So this force has to be twice as big. This is how people can balance on teeter-totters and stuff like that. Like if you have a more massive person and a less massive, the less massive person has to be farther away from the pivot point and they can actually balance. Okay, good. So if you watch that video that I put up on Monday, you can take a hammer, right, and balance it on your finger. You just have to put it at the center of mass to be able to do that. Okay, so you can imagine yourself doing that. All right. So that was 23. So this is kind of a fun one that you can't see. And we're going to do a little bit of estimating with this one. So it says hold your arm outstretched so that it's horizontal, like this. Estimate the mass of your arm and the position of the center of gravity. And there's a little tutor solution part you can take a look at here where the author of the book goes through solving a similar problem. What is the gravitational torque on your arm about this position? So if I'm standing here, my shoulder is the pivot point. There's a center of gravity of my arm, probably closer to my shoulder than my fingertips. So the center of gravity is where the weight of my arm is acting. So there's weight pulling my arm down, a distance from the pivot point. So there's a torque because of gravity on my arm. So those of you that did the lab last week, we did a kind of a similar thing, but we were looking at the bicep muscle. Here we're looking at kind of like the shoulder muscle. So we want to estimate how much this is. And these are different orders of magnitude. So this is like 10 to the power 0, 10 to the 1, 10 to the 2, 10 to the third. So they're all, a factor of 10 apart. So we're just going to get a rough idea. Okay, well, let me draw it out a little bit here. We can put some numbers with this. We probably won't get the correct answer, but we'll get the correct order of magnitude. Okay, so here's my arm. I'd say the center of gravity, and this is my shoulder, it's probably closer this way. So when I was looking at this earlier, I estimated it to be about 1/4 of a meter, so 0.25 meters. That's the distance to the where the center of gravity is. And then I thought my arm, it's hard to do it in kilograms, maybe pounds. Maybe my arm is like 20 pounds or something like that. Probably it's less, maybe it's more, but I didn't Google it. I should Google average mass of arm and see what it comes up with. But I'm just saying it's about 20 pounds or so. Okay, so that's the mass of my arm. And all that mass is at that special place called the center of mass. So this is the weight that's here. So the torque, because of the weight, it's the force, which is mg, and then the distance to the pivot point, which is just r. Okay, so torque is force, and then distance to the pivot point, and I'm assuming these are perpendicular to each other. So the sine of 90 would be 1. All right, so let's put some numbers in, see what we can kind of get here. So 20 kilograms. Actually, 10 kilograms, right? That would be 20 pounds. So 10 kilograms. Okay. 10 kilograms, 9.8 meters per second. And then the distance from my shoulder to where it's acting, 0.25 meters. So whatever this turns out to be. 10, 9.8, and then 0.25. Yeah, so I get actually 24.5 kilogram meter per second squared. That's a Newton times a meter. So if you look at the answers, the one that has the same order of magnitude is actually the first one. It's closest to 15 Newton meters. Okay. The other ones are either a factor of 10 to a little, 10 to 100 too much. So in this one, that's the closest order of magnitude wise. All right, good. Any questions about this one? Now you know that there's a gravitational torque because if you leave your arms out here, you can't do this all day, right? Eventually you're going to run out of force. I don't want to say energy, but you'll run out of your muscles will get tired. That's what I'm trying to say. Okay, good. On to the next one. In this one, it's kind of a similar problem. An athlete at the gym holds a 3 kilogram steel ball in his hand. His arm is 70 centimeters long and has a mass of 4 kilograms. And you can follow those steps from the video tutor solution. What is the magnitude of the torque about his shoulder if he holds his arm straight out to the side parallel to the floor? Okay, so both of those are actually producing a torque. And then there's a part B. And then, so I'll leave maybe part B for you, but I'll set up the first part, then we can take a look at the second part. Okay, so we're holding a 3 kilogram steel ball in his hand, arm is 70 centimeters, and the arm itself has a mass of 4 kilograms. So this is a little more work than the previous one because the person's holding a mass in his hand. Okay, definitely need a picture for this one. So this problem was a little more realistic because I took it into account that, well, this center of mass is probably closer to the pivot point here. The only one way we could actually do the problem that we're working on now is just to assume that the mass is right in the center. They didn't tell us where it was at, but because they didn't tell us where it was at, we're going to have to assume it's pretty uniform. And I'm just going to put the center of gravity right in the center of it. Okay, so the whole length is 70 centimeters. So I'm going to say that the center of mass of the arm is right in the middle. Really, they should have given us a better number than this, but this is what we have to work with. So this is the weight of the arm. And over here is the weight of the, what do they call it here? The ball, I'll just call it. And this is all the way at the end, so 0.7 meters. So really, the way that your arm is connected, there's some kind of muscle close to the pivot point that's providing a torque the other way. Both of these make it rotate clockwise. There's got to be something to balance that, right, if your arm's out to the side. So there's actually a muscle attached close to the shoulder here that provides torque the other way. Okay, so we just want the torque because of both of those. So the net torque because of these would be the torque because of the arm itself plus the torque because of the ball. Okay, and the reason I'm assuming it's in the center is because they didn't tell me otherwise, and that's the only way I could really solve this problem. So this would be the force, which is the weight of the arm, and then the distance from the pivot point to the force, and then plus the weight of the ball, and then the weight of the ball is all the way out here at the edge because it's in the person's hand. Okay, so I'll leave it to you. You have all the masses. The mass of the arm is given. The mass of the ball is given, right? The weight of the arm is the mass of the arm times g. The weight of the ball, mass of the ball times g. And they just want the magnitude of the torque. So the way I have it drawn here, technically the torque would be negative, but they just want the magnitude of it, so you can just put the, it's just a positive number. Okay, good. Any questions on this one? All right, very nice. 48. Oh, there's a part B. So part B, you just have to, actually, you don't have to show it to you again. Part B, you're going to have to do a little bit of, use a little bit of geometry on part B. In part B, they have this at a little bit of an angle. Let me refresh my memory. 60 degrees below the horizontal. So part B, it's the same kind of picture, but this is 60 degrees. So you still have this. This is the weight of the ball, and this is the weight of the arm. The thing that is different is the distance to the pivot point. So what you'll have to do, you'll have to figure out this distance. Right? This is the distance to the ball, the perpendicular distance. Here's the line of the action of the weight of the ball. This is the perpendicular distance to the pivot point. So you know this distance, and you know this is 60 degrees. They tell you in the problem. So you can figure out this distance. It's not 0.7 anymore, it's less than 0.7. Same thing, you'll have to figure out this distance. So this was 0.35 meters. You need to figure out how much this distance is. Okay, so I recommend maybe redrawing the picture and seeing why it's different there. So if you already did the human arm model last week, if not, you'll do it tomorrow. We saw that the bicep muscle, the way that we did it, it connects close to the elbow here. So when your arm is all the way down, there is no torque. And then when you start bringing it more and more horizontal here, the bicep force gets bigger. It's kind of similar to this one, actually. When your shoulder is down like this, you don't have to hold it up because it's down. The more and more you go this way, the lever arm keeps getting larger and larger until you're perpendicular. And that's where the first part's where it's the biggest. And then here, the perpendicular distance to the pivot point gets less. Okay. So when you do this part, here's a little check. Part B, the torque should be less than part A. Okay? Any questions on that? Okay, so work on that one, and we'll send me an email, or you can talk about it next Wednesday too. You got a whole week to work on it. So these problems are scary because there's so many words, right over here on the words part. The lightweight wheel of a road bike has a moment of inertia of 0.097. Kilogram meters squared. Hey Rick, is that a rotating thing handy? The mass is on the edge? I'll keep doing this maybe and you can... Awesome, thank you. So the moment of inertia, that's a measurement of how easy or hard it is to get something to rotate, is 0.097. A mechanic checking the alignment of the wheel gives it a quick spin. We do 5 rotations in 2 seconds. And then to bring the wheel to rest, the mechanic gently applies the brakes, which squeeze pads against the metal disc connected to the wheel. The pads touch the disc 7.1 centimeters from the axle, and the wheel slows down in 1.3 seconds. What's the magnitude of the frictional force on the disc? Okay. So be careful. Down there, there's like a little f, little italics f. It's not frequency. They're asking for how much the frictional force is. It's the same symbol we've been using. Just be careful. Here's a clue. It's measured in newtons. Okay? Excellent. So what Rick has here, just to show you what moment of inertia actually is, these are the same amount of mass. I forgot how much they are. Should we go over here actually? So I don't know how much these are exactly. It doesn't really matter, but they're connected on the edge. So to get this to rotate, it's pretty hard because there's a lot of mass away from the center. You can do it, but it's not easy. This one, on the other hand, it's literally the same amount of mass. They're the same masses. This one's way easier. So what is moment of inertia? It's a measurement of how hard it is to get something to rotate. It's related to the mass. If you made this mass bigger, it would be harder to rotate. It's almost more directly related to the distance, though, because in the formula, it's the distance from the pivot point squared. So if I made these twice as far away, the moment of inertia would be 4 times as much. And then this is a lot harder to rotate. You've experienced this if you've ever tried to push a merry-go-round, and if the kids are on the edge and you try to push it, that's a lot harder than if they all went to the center. Okay, so again, moment of inertia, that's what this is an example of. Okay, so related to mass, but how is the mass distributed? In this problem, they actually give you the moment of inertia, 0.097 kilogram meters squared. Okay? So this first part here, 5 rotations in 2 seconds. We could use this to figure out the initial angular velocity, right? We did a similar problem before. We can figure out the initial angular velocity. Then we go from whatever that is down to 0 in 1.3 seconds. So it slows down. There's an angular acceleration. What causes that? Well, it's the net torque because of the frictional force. So there's a lot of layers in this problem. Okay? Let's see what we can do with this. Okay, so the first numbers that we saw, first of all, moment of inertia, 0.097 kilogram meters squared. Sometimes they just give you that in the problem. Sometimes we'll have to calculate it. More about that in a minute. But we do 5 rotations, revolutions, whatever you want to call it, in 2 seconds. So we've got 2.5 revolutions per second. So we can use this. This is the frequency. I don't even want to write it because we're looking for friction too. This is the frequency. I'm not going to write it. We need the angular velocity that we initially had. So this would be 2.5 revolutions per second. Multiply it by 2 pi because 2 pi radians is 1 revolution. And this is like 5 pi radians per second. Now you can multiply the pi out if you want to. I didn't want to punch it in my calculator now, but 2.5 times 2 would be 5, and the pi is still there. Okay, so we go from this to 0. This happens in 1.3 seconds. Okay, so we can figure out the angular acceleration, right? Okay, so this is earlier in the chapter we did this kind of stuff. So what is causing this angular acceleration? It's a net torque. So the net torque is equal to I times alpha. So this was in the notes from Monday. So if you're wondering where it's coming from, torque is equal to I alpha, just to refresh your memory a little bit. Newton's second law, in the linear world, F is equal to ma. Can't see. So we're used to this. This was chapter 4 and chapter 5. Now in the rotational world, there's a similar equation. Torque is equal to I times alpha. So instead of force, we have torque. Instead of regular acceleration, we have angular acceleration. Instead of mass, we have moment of inertia. So torque is related to force, it's just where's the force applied. Moment of inertia is related to mass, but how is the mass distributed? And then this is angular acceleration compared to regular acceleration. Okay? And then this is equal to, what are the actual forces? Well, it's the force of friction, and then where is it acting? Distance r from the center. They actually tell us r in the problem. 7.1 centimeters, that's where the brake pads actually touch. Okay, so here's the wheel. It's spinning. What actually stops it? Here's a little brake pad with a frictional force. So frictional force, some distance r. That's what's giving us the torque. Okay, so make a note, this is friction, it's not frequency. So frictional force, some distance r from the axis here, and that's given in the problem actually. Okay, so let me recap the problem. From this beginning stuff, we could figure out how fast we're initially spinning, and then the mechanic applies the brakes goes down to 0 in 1.3 seconds. So from this information, you can find the angular acceleration. So why do we need that? It's to figure out the frictional force. Because they give you this, you can figure out alpha, r is actually given, then you can get the frictional force. Okay, so I times alpha over r is equal to the frictional force. Okay? We just want the magnitude of it also. I guess I was assuming it was going one direction, which you don't really have to assume that. So if you happen to get a negative sign the way you set it up, we just want the magnitude of it. Okay? Good. So again, this is given, this is given. You have to do a little bit of work to get alpha, but you can get it from here. Okay, so it's a lot of things to put together. All right, great. Questions on this one? So to have an angular acceleration, you need a net torque. Let me just say a couple of things about the last two without actually working them out. So this one, we have a 240 gram, 21 centimeter diameter plastic disc spun on an axle through its center by an electric motor. And then what torque must the motor supply to go from 0 to 1700 RPMs in 4.4 seconds? So what is the net torque for this one? Okay. So from all this beginning information here, well, let me just put it on a piece of paper. There's a couple of things we're going to have to do for this one. Okay, so in the last problem, they gave us the moment of inertia. Sometimes you have to actually calculate the moment of inertia. So there's a table in Chapter 7 that has different shapes. So I'm assuming that this is just a disk. So for a disk, the moment of inertia is 1/2 mr squared. This is for a solid disk. That's what I'm assuming this is based on how they describe it. So previous problem, they gave this whole thing to us. Here we can actually calculate it. So 1/2, the mass is 0.240 kilograms, right? Change it into kilograms. And then we know the diameter of it is 21, so this is got to be 10.5 centimeters for the radius, right? This part. So 0.105 meters. And then don't forget to square it. So take a look back at that table in Chapter 7 for different shapes. On the test, I'll give you that table if you need it. You don't have to write it on your formula sheet. Okay, so this one, again, you have to actually calculate I. Okay, good. So the torque that we need is I times alpha. So the rotational world is just a little harder every time. In the old days, they would just give you the mass and that was it. Here, they give you the shape, the mass, and the distance. Then you have to do something. You got to calculate rotational inertia. So you can do that. You could also calculate alpha. We've done that before. A couple of problems today. Omega final minus omega initial divided by time. So I'll leave it to you then to get alpha. Okay? Good. So once you do, I times alpha. Be careful with units. That's my last piece of advice for that one. All right, questions on that one? All right, well, let's look at the last one then. So a frictionless pulley can be modeled as a 0.84 kilogram solid cylinder. Okay, that's the same shape that I modeled the previous problem on. 0.84 kilogram with a radius of 0.32. We have a rope with different amounts of tension, as shown. How much is the angular acceleration for this? Okay, let me kind of sketch this one out. They kind of draw it a little weird in the picture. It's really similar to what we did before. This is 12 newtons. This is 10 newtons. It would make it rotate in different directions. And then this is the radius. It's the same for on both sides because it's from the center to the outside here. And we know that this is 0.32 meters. Okay, and they're asking what is the angular acceleration? Okay, so where it all starts really is torque is equal to I alpha. So you might say, okay, alpha, I know I need to know like omega final, omega initial, time, things like that to get alpha. But remember, you could also use this to get alpha. So kinematics-wise, we've done that with alpha before. They don't give us any kinematics information in this problem, so we can't really think about kinematics. But we do also know that torque is equal to I alpha. Just like before, when we had the linear world, a lot of times we'd have x initial, x final, the time. You can get acceleration that way. Or, once we got to chapter 4 and 5, if they gave you the force and the mass, you could get acceleration that way too. Okay, so that's what we're doing here. We're using like this Newton's second law for rotation to figure out alpha. Okay, so torque is equal to I alpha. So what are the actual torques? Just like before, what were the actual forces? Here's the actual torques. 12 newtons at a distance r, because it would make it go this way, minus 10 newtons, and then the distance, same thing, r. And then hopefully we know enough to solve this problem. Again, they didn't give us I in this problem. You have to figure out what I is. So for this shape, it's 1/2 mr squared. So there's more work to be done. You have to actually figure out I. The right-hand side over here, you actually know everything. 12 newtons, r is given in the problem. 10 newtons, r is also given in the problem. So putting it all together then, alpha turns out to be 12 newtons times 0.32 meters minus 10 newtons, same thing, 0.32 meters, and then divided by whatever this turns out to be, 1/2 mr squared. Okay? You might start to hate rotational motion because there's always an additional step, right? More than force, it's where it's applied. More than mass, what's the shape, that kind of thing. Okay, good. Any questions on this one? Good, so if you took this in West Lafayette, what you just had now was like the recitation part of the class where you would meet with the TA or whatever, go over homework questions and anything like that. No questions? Okay, so you got a whole week to finish it up. Don't wait till the last minute. And I thought we could take a look then at chapter 8. So in chapter 8, what we're going to be doing from chapter 8, just the first 3 sections. Okay? Highlighter. Okay, so equilibrium. That's the part of chapter 8 we'll do. There's elasticity. That's the second part of it. We're just going to focus on equilibrium. In a way, this equilibrium part is parts of chapter 4 and 5 combined with chapter 7. It's balancing forces and balancing torques at the same time. So the person here is balanced over center of gravity, right? If the person put their leg this way, they couldn't stay in that position. The center of gravity would change. But right now, this, what do you call a person that wears those kind of shoes? Ballerina or something? I don't know. Anybody know? I'd say so. So the center of gravity must be right here. Forces and torques are balanced. So you don't probably notice this, but as you walk, your center of gravity always changes. If you bend over to pick something up, if I kept going and didn't move this leg, I'm not going to do it, I would fall over because my center of gravity would be outside of my pivot point. So I'd have to put this leg back, right? And then I could actually do it. I'd actually change my center of gravity. So you're constantly changing your center of gravity when you walk. You want it to be over a point of support. If not, then you fall over. So here, center of gravity is over this small point here. Okay, good. So forces are balanced and torques are balanced. As a cyclist balances on his back tire, the net force and the net torque must be zero. So forces are balanced and torques are balanced. Static equilibrium. So if you're building a house or something, you want that to be in static equilibrium, right? If not, the house falls over, whatever you're building. And then again, we're just going to do the first three sections, so we're not going to do this springs part. We just don't have time to incorporate that in. Okay, so section 1.1 through 1.3. It's neat stuff, so I left it on the PowerPoint. You can take a look at it if you have some time. So in chapter 7, we learned to calculate torque. So here it was a line of action of the force and the perpendicular distance to the pivot point. Or you could have used the whole lever arm and then just the perpendicular part of the force. They both work out. So we'll do more with that, really. And then we'll bring in balancing forces as well. So when the net force on a particle is zero, the particle is in static equilibrium. And we saw that before. Forces were balanced. So either it doesn't move at all, or it moves with a constant velocity, no acceleration. Okay? It's when the object has different shapes. Whoops, you can't see that. Okay? So this was just for the point model. When the actual object has a shape, you could have a situation where the forces are balanced, but the torque's not balanced. Like the lower one here. The forces are still balanced. You still got a certain amount of force this way and an amount of force this way, so the forces are balanced, but this would actually rotate. So if there was a pivot point right in the center, this thing would actually rotate. Whoops. Pen. So if you put a little pivot point right here, this thing's going to rotate. Even though the forces are balanced, it has a net torque, so that would rotate. This one, it's not going to move, and it's not going to rotate. So both of those conditions are satisfied. No net torque, no net force. Second one, no net force, but there is a net torque, and it would rotate this direction. Okay? So this is a fancy way of saying, add up all the forces, they add up to zero. Add up all the torques, they add up to zero. Whatever would make it rotate clockwise is balanced by whatever torque would make it rotate counterclockwise. Whatever force would make it accelerate to the right is balanced by whatever force would make it accelerate to the left. So there's no net force. Okay, so here's a hammer that's actually in equilibrium. There's the center of gravity. So that's the point where you could put your finger. You can balance it here if you want to. So that's where there's not going to be a net torque and not a net force. So the amount of force up, if you take NA plus NB, those forces up have to be equal to the weight, which is down. That's balancing forces. And then the torque about the center of gravity from each of those is equal to each other as well. Okay, and you can pick whatever you want as your pivot point, and the torques are always going to be balanced about that point. So there's not one special point where the torques are balanced. There's wherever you pick. More about that when we do some examples. Okay. Some pivot points are easier than others when you do problems. Practically speaking, if you're trying to solve a problem with torques and you don't know a lot of the forces, if you pick the pivot point at one of those forces, then that force doesn't have a torque because it's right at the pivot point. That'll make more sense also when we do some of these problems. Okay, good. So this one's pretty neat. I thought we could just, it says this answer requires reasoning, not calculating, but I think we need to draw it out a little bit. Actually, maybe I could just do it here. So here is 1,000 newtons here, and this whole distance, let's just call it L. Now the scale has a force on this rod that's this way. We can just call it normal force from the scale. And then we can pick this as the pivot point. So the torques are balanced. So you have 1,000 newtons way over here at L. This distance is L over 2. So if you had to guess without knowing anything about torques, you would probably just say, well, if there's 1,000 newtons out there, then the scale is going to read 1,000 newtons, right? That makes sense, I think. You got 1,000 newtons, there's a scale. We don't know anything about torques. The scale should read 1,000. But it turns out it's not going to read just 1,000 because you got 1,000 newtons way out here at a distance L. Here's a normal force here from the scale at a distance L over 2. Because this length is twice as big and that length is half as much, this force is going to have to be twice as big to balance the torques. The torque, because of the scale, making it go counterclockwise, has to be equal to the torque from the weight, making it go clockwise, about that pivot point that I circled. So 2,000 newtons. It seems like it would just be 1,000, doesn't it? But if you really look at the torques, it's going to be more. Okay? So maybe one more step to convince you. Let me go back. So the way that you would write this is the normal force from the scale, that's the force. Where is it acting? L over 2. That's the torque because of the scale. This is equal to the torque from the weight, so 1,000 newtons. And then the distance from the pivot point to the 1,000 newtons is L. So the L's cancel out. So normal from the scale then, you multiply both sides by 2, that's how you get 2,000 newtons. Sorry, the computer is putting those lines in on its own. Okay, good. So normal scale is 2,000 for that reason. All right, excellent. All right, any questions on that one? And let me just say one more thing about this one. So if the normal in the scale is 2,000, and that's up, and you've got 1,000 newtons over here that's down, don't all the up forces have to be equal to all the down forces? And it turns out that they actually do. So there's a force from the hinge this direction. This also has to be 1,000 newtons. So if you actually built this, you've got to make sure that you get a strong enough hinge. Then you got 1,000 down, 1,000 down, and then 2,000 up. And then all the forces are balanced too. Okay, great. Now pretend you made this really, really long massless rod and you put 1,000 newtons there. You might actually break that hinge, right? If you put too much pressure on it, the hinge can't withstand all the force perhaps. Okay, good. So forces and torques balanced. So let's see problem 8.1 real quick. All right, 1 second. So this is actually from homework 9. There's going to be 10 homework assignments, so that should make you feel pretty good, right?